heating and cooling. So here we're thinking we have a some physical object that has temperature, and it's in a system that has a temperature. So we're going to use for this, at least for this topic, we use Newton's law of heating and cooling as the model. And Newton's law of heating and cooling says the rate of change of a temperature, of the temperature of the body, of the object, is proportional to the, if I can spell right, to the temperature differential between the system and the object. So if my system has temperature S and my object has temperature T, say capital T, then the rate of change of the temperature of my object is proportional to the difference in the temperatures between the system and the object. So this is Newton's law of heating and cooling in differential equation form. So let's give myself a little space here. Let's actually solve this. So I note that this is separable. I also note that it is first order linear. So yeah, let's do, since we've done first order linear a little more recently, let's go back and do a separable equation. We'll take that approach. So I can break this up as dt over s minus t with the capital T's equals k d little t. And I can integrate these. On the right, I get kt plus constant. And on the left, I get log absolute s minus t. I note that if I differentiate this 1 over s minus t, I get a negative that comes out, so I need a negative there, which tells me maybe I'll call this constant c tilde, and then I'll call this constant c will be c is negative c tilde. I do this quite often. I'll rename my previous constants so that I can stick with a nice name for my most updated constant. Exponentiating. And I note that e to the minus kt plus c, that's this. And this is just some other constant, let's call it a. I can add t to both sides. I can subtract a e to the negative kt, and I get t equals this. That's my temperature at time t. S is the system temperature. K is this constant of proportionality that will depend on things like, oh, what is it called? I can't think of the word now. The temperature coefficient, now like the specific heat or something like that, it'll depend on these kinds of things. A is just kind of an arbitrary constant that doesn't really tie into the physical system very well. So let's try to get something a little more meaningful for that. Let's call T of 0 T naught, the initial temperature. E to the 0 is 1. So S minus A equals T naught, or A equals S minus T naught. So what do we have? T of T equals S minus A is S minus T naught, e to the negative KT. So everything now is kind of in terms of things that are physically meaningful. And we can see that if the temperature of the item, T naught, starts out at the system temperature, then this contribution this factor here is 0, this contribution is 0, and the temperature just stays at the system temperature. So if T naught equals S, then this factor is just 0. If T naught less than S, well, if T naught is less than S, what do we get? This is did I get a sign wrong? I feel like I got a sign wrong here somewhere. Yeah, I'm thinking if T naught is less than S, then temperature should increase. Oh yeah, okay. Yeah, I'm just having a brain fart moment. Attribute it to not feeling too well. Thinking in terms of what I expect from the differential equation rather than from the actual solution. So yeah, if T naught is less than S, I start out with S minus something positive. So I start out with something below S, but then this contribution decays, so I increase up to S. And vice versa, if T naught was bigger than S, I would start out with S minus something negative, so S plus something. So initial temperature being bigger than S, but then this positivity effect would decay over time to 0, and I'd approach system temperature. So I see that over time, this contribution decays to 0, even if my initial temperature is not equal to the system temperature. So over time, my item that I'm studying approaches the system temperature. So one thing that we might recognize as an assumption here is that system temperature is held constant intentionally. So we're thinking of like a refrigerator or something like that, not like an insulated box, right? It's not like I have an insulated box that's 30 degrees Fahrenheit right now, and I put something in the 70 and just close the box. Well, then the system temperature will rise as the cup of coffee cools. I'm thinking of something like a refrigerator where I'm, say, holding it at 30 degrees and allowing that item to approach that 30-degree temperature. So that is an important detail. Or we can either think of deliberately controlling the temperature, or we could think of an item that is not sufficiently large to impact the overall temperature, right? If you had an enormous warehouse that was 30 degrees and you had your cup of coffee that's, whatever, 100 degrees, your cup of coffee isn't going to heat up the whole warehouse. So in that case, you could probably reasonably apply Newton's law. But if you had a little cooler that you had cooled down and then you put your cup of coffee in it, well, you can't consider the system temperature as being constant in a case like that. Okay, let's, I think maybe we'll leave Newtonian mechanics to next time. But I think we'll try to get through this problem. Get my notes shuffled around over here. Okay. So let's look at this problem. So CSI, crime scene investigation, shows up to a murder scene at 9 a.m. and they measure the temperature of the body. At 9 a.m., it's 33 degrees Celsius. They wait an hour, they measure it again at 10 a.m., it's 32.5 degrees Celsius. And the ambient air temperature was 8 degrees Celsius and had been a steady 8 degrees Celsius for quite a while. If we assume that Newton's law of heating and cooling applies to this situation, that it's a reasonable approximation, and that normal body temperature is 37 C, at what time did the murder occur? So that's what we want to find out. So let's let T be the temperature of the body. And we have dt equals K times, and here the system temperature, the ambient air temperature was 8 degrees. 8 minus T. And this tells us that T equals up here. S is 8. I can draw 8. I was getting ready to say S and trying to draw 8, and I drew an S. 8 minus, and let's just put an A in here, AE to the negative KT. So this is my model for capital T. So I see that I have two unknowns. I have K and I have A. And that's actually why I need not just one, but I also need a second constraint. So kind of the, if I only had one unknown, I could probably get away with just one constraint. But since I have two unknowns, I need two constraints. So what can I say here then? Let's draw a picture. So the first thing is we have to index T, index little t. Let's let little t be the time since midnight in hours. And we have t equals 0 at midnight. T equals 9 is 9 a.m. 10 a.m. is t equals 10. And then t star, let's call time of death. And this could be, here, or it could be here. Right? It could be a negative number, meaning that the death occurred before midnight, or it could be a number between 0 and 9. So t star is in negative infinity up to 9. So we definitely shouldn't get a number like 20 or something, but this is quite a wide range, but at least we have a constraint on where we think t star will be. I have two constraints now that I can write a little more formally. T of 9 equals 33. T of 10 is 32.5. And T of t is this. So on one hand, I have my constraint equations. On the other hand, I have my requirement from the model to match everything up is 8 minus a e to the negative. So here is when t is 9, 9k. And this is 8 minus a e to the negative 10k. All right. So what can I do here? I have two equations of two unknowns, not linear equations, but they're not too bad, right? The first thing I might want to do is just subtract my 8s over. And let's see, what does that give me? 25 equals negative a e to the negative 9k. And I have that, what? 24.5 equals negative a e to the negative 10k. I can divide these two. I get 25 over 24.5 equals the negative a's divide out. I have e to the negative 9k over e to the negative 10k, but that's e to the 10k over e to the 9k, that's e to the k. So that tells me that k is log 25 over 24.5. And I think, yeah. So this is about 0.020203. Or exactly, it is log of 25 over 24.5. So I've got k. How do I find a? I find a, let's take the t of 9 equation, because it's simpler. Actually, let's take that equation, because that's even simpler. I have 25 equals negative a, e to the negative 9, log 25 over 24.5. And what do I need to do here? I need to get that exponent just as a log, e to the log of 24.5 over 25 to the 9th power, right? That negative 9 in front of the log can pop up as a power inside the log. We flip it to make it a positive exponent, and that stays in the log. And e to the log of stuff is just the stuff. So 25 equals negative a log of 24.5 over 25. Oh, not log. Making all kind of mistakes today. Maybe it's good that I'm planning to end a little early. Negative a times this to the 9th power. So what does that tell me? That tells me that a equals, that's going to be negative 25 times 25 over 24.5 to the 9th. Let me make sure that in my notes I did it the other way. So I did it with the other equation. So hopefully this a is the same as the one that I got in my notes. Okay. So we did all that work to find what? T as a function of only t. So now I know what a and I know what k are. They're kind of annoying numbers, but they are just those numbers. So I see that t of t equals 8 minus a e to the negative kt. Or it's going to be 8 plus a, and then e to the negative k t. And what I actually see here nicely is, right, this is k, but I have an e to the negative k t. So this is going to look like, well, this negative comes up, makes it log of 24.5 over 25. And I have e to the log of 24.5 over 25 to the power t. So I can probably go a little further with this to simplify. I see if I make this a, let's see, let's make this a negative 9, and that flips those. Okay. So I think that's about as nice as we're going to be able to make it look. I mean, it is what it is, right? when you get to this point in your math career, sometimes the solutions, aren't super nice looking, but that's kind of the price we pay to have interesting problems. So this is the temperature at a given time. Now, what's my goal? Find T star such that T of T star equals 37. So the idea is that we have, normal body temperature is 37. When the person was alive, they're maintaining their body temperature. When they die, they stop maintaining their body temperature, and then just kind of follow Newton's law of heating and cooling. That's the assumption. Again, is it a perfect assumption or not? That would be, certainly up for debate between forensic scientists. But we're making that assumption here. So let's find such a T star. So I want to set 37 equal 8 plus 25 times to the power T star minus 9. How do I solve this? Well, I got to get my exponential bit by itself. So I got to subtract 8, divide by 25. So I got 29 over 25. To this power, which I don't have room to write. Let me bring it over here. I can log both sides. Bring the power down. I can divide by the log. Add 9. And that should be T star. If I didn't make any arithmetic errors, that's what we should get. Let's bring up the calculator and cross our fingers. So I've got log of 29 over 25 divided by log 24.5 over 25. We do that. And then we add 9. So this is telling us it's, okay. So we add 9 and we get 1.65. So it's 1.65 hours. Remember what T star represents? Or remember what T represents? T is the time since midnight. So T star is the time of death after midnight, hours after midnight. So that is going to be like 1. And so we come over here, we subtract 1, multiply by 60. So it's going to be like 1:39 a.m. I mean, that's what we estimate as the time of death for this individual. So a lot of moving pieces, but again, how much of this was differential equations? Well, this is something that we see often in differential equations, is that the problems we're trying to solve might take like, a whole page or something to solve for a complicated problem. We have one very key step. We couldn't have solved this problem without, this step, without this model. We have maybe one or two very key steps where we apply a differential equation idea. But there's also, it's very important for us to understand that there's a lot of surrounding ideas as well, right? Ideas from trig or from mathematical modeling or from algebra. And So we might see that, 90% of the actual work that we do or the things we write down maybe have to do with, you know, algebra or solving systems equations or, arithmetic manipulations of things to make them look simpler or more amenable to solving. We had our, important differential equation idea, but a lot of the ideas were things like setting up our variables in a meaningful way, getting an idea of what maybe some bounds on the solution are to be able to check the reasonableness of our answer. Maybe checking units in a different problem. Doing the algebra and arithmetic to solve for T star. So, right, that's something that you'll see a lot in differential equations, is that it'll feel like a lot of algebra, a lot of arithmetic, a lot of maybe trig or some of that kind of stuff. But there will be a line or two that is a very key part of the solution where the differential equations comes in. So we're not often doing 30 lines of differential equation stuff. A lot of times it's 28 lines of algebra, and then 2 of those lines were important differential equations ideas. So any questions on this one? Okay, I think I'm going to end a little bit early, just because, as I kind of mentioned before, I'm not feeling all that great.